So now we have seen how then nanotechnology was from the ancient times, and now how it has evolved, coming from all the chip foundries, all the mobile phones we are using. Right? How do you buy a mobile phone? How do you buy a mobile phone? Every 6 months, mobile phones are coming into market. Right? Yes. No? Yes. So generally, how do you buy a mobile phone? It's an interactive session. Please. Huh? How do you buy a mobile phone? Yeah, good money. Then what do you see on that? So directly diving into the technical things. Processor. Okay. So you get an Oppo phone, say for 25,000 with the same features, and you have a Samsung phone with the same features for 50,000. Same features. What makes that difference? How? On the processors, right? You are going to get the same display, curved display, this much amount of RAM, this much amount of this, storage, 128 GB, gaming time, fast charger, everything. But what is a trade value? They use some other processor and Samsung use Snapdragon processor. Or they may use 657 and 659 and other thing. Right? You guys are more knowledgeable on this all processor things from Snapdragon. Every YouTube they have this. So this is a basic thing where they compare processors using certain things, right? So they give you a lot of specs. So it all comes down to that point where a processor makes a difference. What we are talking about processor is what you guys want now is you want to have a long run time, less charging time, large screen time, less heat. How many of you here use Redmi phones to iron their shirts? It happens, right? No Redmi fans here in the house. I use it because it generates a lot of heat, right? If you watch a 8 hour long series, it's ready for an iron box. Yes, no. Yes, no. Okay. So it all depends on how things have been manufactured from step one to the step later, right? Now, what exactly market is doing here? We are all talking about the end of Moore's law, beyond Moore's law, beyond CMOS computing, Intel, IBM, many competitors. Now you have a nothing phone. It costs very nothing and it have all the features in it. Right? No nothing phone fans here. Oh god. You guys are out of trend there. Okay, that's good. Next one. So let us understand size. Okay, the same picture. You see how we are going to see nano. This is going to be what the technical definition it was in the first one. I said that we will explain you graphically. You can see that this 1 meter and this is 10 centimeters. The same picture zoomed in. Next one. Further zoomed in, and this is 1 centimeter. Further zoomed in, this is 100 micrometers. Further zoomed in, this is 10 micrometers. Further zoomed in, this is 1 micrometer. You can see all imagine from the top, very big picture to this, right? This is 100 nanometers. Next one, this is 10 nanometers. So this is what we are going to talk about. You can see from a bigger picture to a smaller picture how this top to down approaches, right? Next, next. So, right, how many Marvel fans in the house here? Oh God. No faculties are here. They won't mind if you talk about cinematic things here. I assure you. No Marvel fans in the house. There's no interest in the presentation. Any Marvel fans in the house? Guys, good. Okay. Next now. So here we are going to talk about the basic digital logic circuits and systems, the basic logic gates. It may seem completely irrelevant now with the topic, but once I finish next 5 slides, I'm going to tell you how this is ruling the world, ruling the entire world on rebooting computing, the modern AI. Okay, I want your attention on this. This is going to be a regular classroom and gates or gates, but trust me, if you understand this, you are going to have a very big understanding of what's happening in the rebooting computing world and how you can be part of it. So you know, right? This is the first one is the basic AND gate. How many first years here? All are first years? Oh, then great. So you might have seen this very fundamental. What is an AND gate? It does A and B, right? Only gives you, if there are two positives, it will give you a positive. Otherwise, it is negative. Okay, positive, negative is then 0 and 1s. In digital circuits, we consider it. Next is an OR gate. OR gate is it can either A or B can be true, output will be true. Right? This is an OR gate. Next one. AND gate is it is an invert. So A is 1, A bar is 0. If A is 0, A bar is 1. So this is an invert. So these three are called the fundamental gates. Remember, and or not, three are fundamental gates. Then there is also a term called universal logic gates, right? Many of you might be knowing it. NAND, NOR is a universal logic gate. Why it is a universal logic gate? And first, what is NAND? NAND is an not operation of AND. AND with an inverter gives you NAND. Why I told you AND or and not a basic gates, you can almost build any circuit on this world using the three gates. And or not. You can build almost any circuits for your computer, for your mobile, any big circuit you can build with and or not. But the drawback is when you use and or not to build any circuit, there is a complexity involved in it. The what four things we remember in mind: low power, energy efficient, small area, right? That's what we see in a mobile phone, right? It has to have my charging time has to be longer. It has to have fast charging. My charging should last longer, and my screen time should be higher, right? All boils down to 3 points: low power, energy efficient, area efficient, high performance. So all these are four are the key mantras to decide any rebooting computing architecture. As I said, and or not can be used to build almost any circuit, but these four mantras will get lapsed when you use them. So we have to see alternatives of using this, because when you want a NAND, you want to have an and a NOT. So it basically gives you two gates, right? Area wise, it is complex. To reduce that complexity, we are going to bring in the NAND gate, which is serves the same function of AND inverted NOT is a NAND, right? So here you can see the truth table, which is completely an inverter to of an AND gate. Here, when there are two positives, it is going to be negative. And all other case, it is going to be positive, right? That is an AND gate. And the NOR gate. NOR gate is OR with NOT. That is an OR gate, right? You can see what is an OR gate, and you can invert it to an OR gate. You find only when there are two negatives, it will give you a positive. All others it will be negative. Okay. So this is a NAND and NOR gates. As I said, these are universal logic gates. In next slide, I will tell you why I say this is a universal logic gate. And with the first slide itself, we can build almost any circuit. So if that is possible, with this slide, it is almost done, right? With we are saving area as well. That is the key point. Next. And there are also two other exclusive gates, which is called exclusive OR and exclusive NOR. So same OR gate, we will be doing the exclusive, and NOR gate we also will be exclusive. Where in the XOR gate, right, only we have two positives, where A and B cannot be the same. That will give you an XOR gate. And in XNOR gate, we will have two positives when A and B is same. 0, 0 and 1, 1 only we will get a positive value. All other cases we will get a negative value. Next one. So now we are going to have from universal logic gates the definition of basic gates. As I said, with a NAND gate, right, we can have a NOT gate. How we can have a NOT gate? We can use a NAND gate as an inverter where A and B are connected together. When A is equal to B, that is 0, 0, you have a 0, it will give you 1. NAND of 0, 0 is 1, right? And same thing you are going to have NAND of 1, 1 is going to the invert 0. So a NAND gate, when you have an A and B combined together, it is going to be acting as a NOT gate. Understand this, right? Now using this, now we are going to show how using a NAND gate, an OR gate can be when you have invert the inputs of NAND gate, A as inverted as A bar and B bar, it will give you A plus B. That's what an OR gate. So for inversion, now we have the NAND gate, right? We are not going to use a traditional NOT gate. How you invert? You club the A and B of an NAND gate, it serves as your NOT gate, right? So same, the first whatever I have shown you in the NOT gate, we are going to use 2 times as an input for that NAND gate. Okay, so A is inverted as A prime and B is inverted as B prime, and A prime and B prime as a NOT gate will give you plus A plus B, right? So this is an OR gate derived from the NAND gate. And now we are going to see how an AND gate is derived from the NAND gate. Figure 3 you can see, right? We wanted to have a NAND gate A and B and its output is inverted. First, to attain the OR gate, you are inverting its input. Now to attain the AND gate, you are inverting its output. So A and B is connected to an AND gate and you are inverting that output. That you are using the same NAND based NOT gate and you are getting AB. As I said, this is the universal logic gates functionality to be used for this basic logic gates. And we can also write as NAND gate as shown as inverter and an OR. Same NOR gate can also be shown as inverter. When you add 0 to it rather than 1 gives you and 0 gives you OR using NOR gate. Next. Okay. So let us take a simple example. Okay. You want to go home. What are the possibilities that you will go home? Your output is say F is go home. Okay, you have 3 variables A, B, C. A is Sunday. You will definitely go home. B is holiday. You can go home with a condition with C that there is assignment. C is assignment. C bar is no assignment. So you will go home if it is either Sunday or holiday with no assignment. Right? Understood? It's a simple use case of how circuits can be clubbed into a real-time problem. If you are going to go home, if it is a Sunday or holiday and exam not of exam, no exam. How do you represent in terms of and or equations? F is equal to A, that is R plus holiday, B, no exam, holiday and no exam, B dot C prime. F is equal to A plus B dot C prime. The equation looks very simple. Many of you have heard these equations many times. But one real-time analogy what you can relate with this, you can assume that F is a go home, A is a Sunday, B is a holiday, and C is assignment, and you invert assignment, no assignment, and you can go home if it is a holiday and or holiday and no exam. Okay, this is how you want to relate your circuit to real-time examples to understand how you can break complex circuits to get into the basics using very fundamental gates. Very, very fundamental gate and or not. We have used all 3 in this. Okay, next one. So as I said, and not and all of these gates, using this only you are going to build any complex computing. Say CMOS, whatever processor we are using is CMOS, everything is there in the models. But when you want to think beyond CMOS computing, rebooting computing, nanomagnetic computing, you want to start from these gates with all the beyond CMOS applications. Either use in magnet or neuromorphic computing using brain synapses. You want to start with this AND or NOT gate, NAND and NOR gate, right? That's what the basic understanding is. Every adder, every multiplier, every convolution, everything can be built using these gates. That's what I said. This slide, if you understand this is going to rule the world. And you don't believe me, this is your basic fundamental slide. Maybe you have gone through this in UG first year. And believe me, it's a survey report that few thousands of researchers, that is 30 to 40,000 of researchers around the globe, are doing their PhD with this one basic slide. How interesting it is. This is one classroom slide which you have gone through in your undergraduate first sem or second sem. But after BE, MTech, PhD, few thousands of researchers around the globe are doing their PhD and postdoc work, and industries are working on it with this basic fundamentals. This is very important, right? You have to understand how it is. As I said, A plus B dot G prime, you should never forget how this works in a real time. The same principle applies from traffic light signal to the recent launch of ISRO's Chandrayaan. All are connected. All are basic circuits if you break down into it. Right? All bigger architectures you can break down into smaller modules. One thing you want to do is understand its real time analogy so that you can contribute to. As Dr. Perumal was mentioning, we wanted to contribute to nanotechnology magazine from being a BJT undergraduate students. This could be a start who are interested. Radio show could be a start who are interested, right? So let's get into some advanced things. All we heard, all this wearable electronics, right? Yes, we have all the smartphones embedded within the. We have sensors embedded within our dress. Is there in the market for some time and it's commercialized. Now the future is edible electronics. It is mainly going to have its feature in medicine, biology, nanomedicines. Next. So you eat a pill and it has all the sensors embedded in it, and it's going to monitor you from inside and tell the outside doctor what is happening within you and what diagnosis can be done. Right? Wearable to edible electronics. This is going to be the future. And when edible electronics comes into the picture, all the standard activities comes. Next. So you can see how what is the bigger analogy to this micro and optical electronic components to for this light properties. We are also dealing about materials there, and materials approvals is a separate task for the standardization, and we are having the systems approbation. We also need to have communication strategies, right? Something has to be communicated outside, and some decision has to be communicated inside, and we need to have power supplies, right? Say as example, we need to see how it can fit in and where it can generate energy harvesting by a fluid motion inside your digestive system. It should be able to generate the piezoelectric energy. And finally, the sensors to sense a particular task. So this is one another emerging field where the wearable electronics has moved to edible electronics for the sensing purposes within the human anatomy. Next slide. Next. So this is STM image of a nanocore molecule and the 4 carbon 60 molecules making up a nanocore, which is easily visible, right? So these are the applications of nanotechnology. Every application here has its real terminology. Maybe we will discuss in detail in other presentations on this. As sticky as GCO, right? But 10 times smarter. How GCO is coming to a real time analogy, we can think about it. Like I said, digital circuit can be combined with the real time analogy, right? Next one. So these are some of the intervention of nanotechnology in agriculture and allied areas. So where people are being working on this. Next slide now. So this is one of the recent findings on sub-generation, sub-nano sensing using graphene. Graphene can heal the cracks. Graphene are using for humanoid robotics that when it is a harm, it can create reheal itself. So they are trying to use this as an artificial skin for people who are met with this fire damages and have many other cases. Graphene can heal the cracks by themselves. This is proved by researchers from IIT Hyderabad on Samudra Debra and group under the Professor Amitabh Chadi. Next slide. So this is how, and there is another interesting example where this next, yeah, cardiac health monitoring. You can go, ma'am. Next. So we wanted the patients want to wear the CCG monitoring device, and it has to be a handheld device. It has to read their ECG properties, and it has to send an alarm when there is an abnormal case, and immediately it has to go to the doctor to try that it's a fake alarm or it's a true alarm, and it has subsequently a decision has to be made. Right. This is one another example where they have reduced 32 nano things to 6, where they can collect the CCG, this turn electrodes on their body. Next one. So, right, why we wanted to reboot computing? Why we want to think beyond CMOS? We are happy with whatever we are having right now, right? Mobile phone is working fine, laptops are super fast. But why we need more fast, ultra low power, energy efficient, right? Why rebooting compute? Because we are aiming for better technology nodes. We want to upgrade ourselves for every 6 months. So, right, people are thinking how we can make energy efficient circuit from the circuit perspective. MIT professor, right, Professor Anandapur Chandrabhashan's group, who is also a dean there, their group is exclusively working on energy efficient computing for 3 4 decades. Still, they are working on energy efficient computing circuit. Then you can understand its importance and its role in the next coming generations also. It does not stop anywhere. Energy efficiency has to be, computing architecture has to be evolved, and people have to do research on it. This is where the term rebooting computing comes into the picture. This is a term first used by this IEEE working group for rebooting computing, and later they started as a community for this IEEE rebooting computing. And they also have a conference on international conference on rebooting computing to bring it the umbrella houses many things under this rebooting computing. Whatever comes beyond CMOS, more than more, everything under this beyond CMOS computing. Next. So this right, everybody knows, or most of us know. This is a traditional Dave game, and how this is an IBM made. They have using this quantum dots. They have reproduced this Dave game to put an efficiency market strategy for their quantum computing. And right side you can see spins dangling around. Right, what is that? It's a majority logic gate which spins. When you have spin up and down, here it is represented as blue and red. It contributes as a majority logic gate. Whatever we talk about this and or nine or this also is a majority logic gate in CMOS, right? Same way we are going to deal with the spins. How this majority logic gate can be constructed. Next one. Next one. Yeah. Next. So in 1959, right, Richard Feynman said there is plenty of rooms at the bottom. And he also wanted to have this entire encyclopedia right in a small rise using this nanotechnology tools. I said, right, he's a visionary. Before the term nanotechnology was there, he envisioned things with nanotechnology, what nanotechnology can do. And now we are having all the state of the art sophisticated instruments. So we should be able to explore more things. No Marvel fans in the house, so this slide is not that interesting. You see this, right? You know, Endgame and all this quantum stuff they have shown in this Ant-Man and Quantumania, Vast. Do you think all these are real quantum things which can rule this world, or at least in the next 2 to 3 years, 10 years, it can come into real commercialized products where you can do things using this quantum and change the timelines? Anyone who thinks it is possible? No, all these are fictional quantums. Don't go beyond this fictional quantums. And what real quantum is, as part of RSL quantum, we fabricate quantum dots and we do this things. So this is another important thing, that how particles react with light, and this is very important. You will see in the upcoming slides how a quantum dot reveals different colors when we reduce its size from the bigger to the small. Right? Next slide. Next. So here we will be talking about more deeply into this surface plasmon properties. You will also see this band gap, how it affects your colors. Next. So you can see, right, the band gap increases as particle size decreases. And the first one you can see the red, and the last mod you can see the blue. So this is going to be a very important property for using this quantum dots. And many of you have heard here this quantum confinement in many movies. But what we really understand is next slide. How it can, what is quantum confinement? See, you can see the right bigger ball, right? Bigger ball is 7.5 nanometer, not less than that, not greater than that. The right side is green ball, right? It's 2.5 nanometer. You can see it's different wavelengths of light emitting. The red with 555 nanometer and the green with 650 nanometer. When a quantum dot reacts with light, based upon its size, it reacts differently. It's a quantum confinement. Next slide. This is the quantum dots next slide now. We are going to talk about 2 to 10 nanometer of size, and you can see the how the energy gap, band gap varies for three different sizes. The first one you can see for the red, next one, yeah, green and the blue. You can see how the band gap varies. That is the main reason, and the size of the quantum dot, which you can give different colors, emit different colors. Next one. So this is a traditional slide which I used to explain interlayer exchange coupling using biryani. So next slide now. Don't quote me anywhere in any technical meetings, but it is you can use to understand how an interlayer exchange coupling can be used as you are cooking a Hyderabad biryani. Next slide. So here, right, we are going to explain this interlayer exchange coupling, which is an interaction between these magnetic layers, and this plays a crucial role in this magnetic devices, magnetic recording media and spintronic devices. And this coupling can be explained. We are going to draw a parallel line between how hydraulic biryani is cooked and what interlayer exchange coupling is. Next slide. So we are having layering ingredients in both the things, right? In biryani also we have various layers of ingredients, and in interlayer exchange coupling, right, we have materials with magnetic layers. Each layer represents a magnetic region. And next we have all the spices and flavors, right? In biryani we have spices and flavors. In interlayer exchange coupling, the properties of the magnetic layer. So magnetic moments, spin orientations, all. Next. So next is they assemble together, right? And bottom whatever is there, it has traveled throughout. Same in interlayer exchange coupling, right? It allows the magnetic moments of adjacent layers to interact with all other layers, increasing their alignment also. Direct analogy. Next. So as you see, whatever is in the bottom, you get it the top layer in the Hyderabad biryani. Same ways you energize the bottom layer and it is transferred to the top layer. Next slide. Next. Yeah. So as we know, why we wanted to bring in this new terminology and why we wanted to think beyond CMOS. With all this technical defects coming into the picture, we cannot get go beyond 5 nanometer, 3 nanometer. Not only with technical limitations, but also with the foundry cost. Right, every time a new technology is adapted, foundry has to invest huge crores of amounts into it. So there is also a technical limitation as well as marketing cost. So with that, we needed to think about spintronics and nanomagnetics for this processing information. Next slide. Next. So as I said, the cost wise to move from the 7 nanometer to 3 nanometer, you can see the skyrocket cost. So people wanted to stop that and think beyond also, rather than having technical difficulty. Next one. Yeah, next. Next. So we have been talking about all these batteries, phones, right? We wanted to have more energy efficiency. So this is the right time to think beyond CMOS, and we wanted to see how nanomagnetic computing can achieve this purpose of having higher energy efficiency, area efficiency, low power, and high performance. Next one. Yeah, next. So as I said, this term was first coined by Professor Peter Denning in 2009 as part of an IEEE working group, and then later Professor Tom Conti at 2012 he took this term into this IRTS International Roadmap for Devices and Systems. They say how the technology is evolving and what is the technology is evolved. So I'm happy to share that one of our works have been included in this International Roadmap for Devices and Systems for this basic fundamental work on nanomagnetic based majority. As I said, the basics are going to rule the world. The basic fundamental majority logic gate proposed by our group, with me as a lead author, has been included in this international roadmap for devices and systems. So that's just the road clear that this is one path under this rebooting computing umbrella where we wanted to pursue compute taking this nanomagnetic quantum computing. Next. So in this beyond CMOS, right, we have three individual things. One is emerging architectures, emerging devices, and emerging materials. First, right, from the materials perspective, we have been working on this graphene, as all are aware of this carbon nanotube graphene, right? Graphene is not by default magnetic. We made it magnetic by giving its properties to have its applications in nanomagnetic. We played with this E and T to make it magnetic. As I said, the band gap, right? In the previous quantum dots, band gap engineering is very crucial. And comes the emerging architectures. You wanted to have these gates, right? All these gates build up into this adder, multiplayer, convolution. As this convolution goes into this deep learning or these neural networks, whatever today's AI, we use ChatGPT, right? It is used trained with data only till 2020. All this pre-training, post-training, everything is boiled down to the neural networks, deep neural networks, convolution neural networks, spiking neural networks. We wanted to achieve that neural networks. We break down that into convolution operation. We further break it down to multiplier. Multiplier is broken down into adder. Adder is broken down into a majority logic gate. Majority logic gate is broken down into a universal logic gate, basic circuits, and are not man now. You see the connection, right? Both top to bottom and bottom to up, top down and bottom up. You see the connection, right? How a bigger picture is broken down into a smaller, and using small, you are building a bigger picture. So these are the advantages of computing with nanomagnets. We wanted to have its energy minimization. As you know, magnets have this remanence properties. What is that? And it is non-volatile. It remains its states even when the power is turned off. So your normal computer does not do that, right? If you put in the hibernate mode, it will be. But when you shut down, you have to fresh start. But it will be in hibernate mode even when it is turned off. Simple analogy. It's not a technical concept, simple analogy. So remember, to keep you remember what nanomatic logic is. Next. Next. So while doing this, right, as we are talking of all the chips we have in the microprocessors today, we need to have this nanomagnetic logic into the chips. But what stops it coming into the chip? In fact, you can energize the nanomagnet using AFM bit. But when you want to have it on chip, you need to have on chip clocking mechanisms. Right? Traditionally, people use copper. Copper is not not in the nanoscale. When you reduce that one copper to a nanoscale to a size of a nanodot, you get quantum tunneling. So you want to think of alternate materials to do this on-chip clocking. Replace copper with graphene so that you can have more number of nanodots onto it. And a vision, we can dream that to having on-chip clocking. Next. Next. So as I said, we made this graphene magnetic by tuning its electronic and transport properties. And we have also envisaged a processor where keeping up your laptop, keeping up your mobile phones, that can be converted into its energy using self-energy harvesting. Next one. So when you are talking about graphene, fabrication wise also it's important, right? There are fabrication facilities at IIT Bombay, IIT Madras, and we have used at IIT Bombay nano fabrication facilities. There we have fabricated graphene nanotubes up to 300 nanometer size. And we have characterized it to get its electrical properties, put it into a parametric model using ANSYS magnetic simulation to see how it can fit into the real world data. And we have developed a model system framework where from the start it is a multi-interdisciplinary field. We have physics involved, we have materials involved, we have electronics involved, we have architecture involved. Finally, we are trying to showcase a system for rebooting computing using nanomagnetic quantum for modern AI and edge applications. So we have been trying to analyze it from each and every user perspective. This is a completely bigger picture. I'm sure many of you may take time to get into this, but try to understand the terms what I'm using so that you will be habituated with it. And if you are interested, you can go back and dig deeply into it, or you can connect to us. We can discuss more on next week. Yes. These are some technical things of the graphic application which I'm not detailing now. Representation of how silicon dioxide graphene and mixing process. Next one. Next one. So characterization, and we have this plot for this VA plot. During most of the first year students in the second semester will be knowing about this VA plots, right? So these are the tools what we have used and what are the procedures for using this. Next. Next. Yeah, next. Next. So as I said now, graphene is everything. But you want to have nanomagnets on top of it. You know what graphene can generate the electric field to convert to an ion field. And you know the energization of this nanomagnets. How this graphene can energize these nanomagnets based on top of it to drive information. Like how a magnetic computing takes place. You have two nanodots placed sidewise, and you can have an antiferrometric connection. And you have placed it top, you can have ferrometric. That is 1 to 0, there is 1 to 1. Parallel and antiparallel. Next. Next. So there is an interesting work from other group. Using graphene itself, they have made it into a bow tie scheme and they use it from upload. They have not made any properties out of it, like we made it magnetic. We use it as a clocking material for nanomagnet. But they use graphene itself to have computation performed as a majority logic gate. They have this bow tie scheme combined to it using this ABC and they perform this NAND operations. You can see, as I told, every paper, every researcher who works on all advanced concepts today, we want to have this table in their paper. You see the connection, right? Basic fundamentals, right? But you will use it every time for your advanced concepts to develop any advanced models, to commercialize any product to the market. You assume we have a good number of patents on this nanomagnetic computing. I'll be presenting this. Next 5 to 10 years, you can see a nanomagnetic processor in a hand. That's going to be a reality. Already industries have invested a lot of money in R&D and they have products developed, testing for commercialization, and soon it is on the roadmap to be unveiled to the public. The next 5 to 10 years, it's no wonder you will have a mobile phone or a computer with a nanomagnetic processor in it. That's going to be the next one. So, right, as now we have seen from the materials perspective, first like I said, materials, architecture, devices. Materials we have covered. Now we are going to talk about architecture. From material also people have been working with architecture. Now what architecture we have been talking about? We know all this speech and face recognitions and all this IoT enabled device, but all the edge computing devices that has very low power. Remotely you place a sensor in a farmhouse, you have very limited power and very limited bandwidth to upload all the data to the server and take it, compile it, work on it. Right? On that place itself computing has to happen. It is not like no more uploading to the server, process it later and get back. Everything has to happen at that place for remote locations. Right? Edge computing AI. Next one. So we aim to have AI computing on the edge with this approximate nanomagnetic logic deployed on MAC devices. Now as I introduce another term, approximate. What do you mean by approximate computing? Right, say if you know a truth table of an AND gate, right? We know truth table of an AND gate, and there is whatever you get a same, it is an accurate AND gate. And if you have any values changing, okay, it is an approximate. Say with AND gate, NAND gate, it will not make much sense. But you when you talk in terms of adder, let's go a level bit up. Okay, for accurate adder, you need to have 3 majority logic gates. Say majority logic gates, even in CMOS, it is 3 majority logic gates. Using nanomagnets, 5 magnets per majority logic gate and 50 nanomagnets for accurate addition, 100% results. But what is approximate? You use only 2 majority gate to get 75% accuracy. One output will be wrong. See, what is the reduction of the area? Area reduction is from 50 nanomagnets, now we are going to use only 10 nanomagnets. This is called approximate computing. Reduction in terms of resources with accuracy which can be compromised for all machine learning applications. There is not required 100% accuracy. There are many applications where accuracy level of 50 to 80% is okay. For that applications, if we can bring down the area and energy efficiency half by half, then it's a great achievement. Which serves the purpose. Low power, energy efficient, high performance, area efficient. This is our 4 top mantras, right? Nanomatic computing is already solving all of this, and when approximate computing also solves all of this, Why don't we combine this two? Approximate nanomagnetic. We will have nanomagnetic computing working as an approximate circuit. So further it will add to your four bandas. Low power, energy efficient, area efficient, high performance. Next. So it started in 2000, and how you can see first it was introduced, the basic coupling was introduced in 2002. The first majority logic gate was took 6 years of time from 2000 to 2006. The first majority logic gate using nanomagnets took 6 years of time from its initial finding, right? And then started from 2010, 11, adders came into the picture using this nanomagnetic logic. From 2011 till date, we have many adders using different nanogates. The state of the art is adder can be comprised only with 4 nanomagnets. We have proposed that and modeled that using only 4 nanomagnets, we can have an addition done. Next one. So, can I take 10 more minutes? So we are going to see about this MQC working principle. How does this work? So these are the majority logic gate. All three does the same thing, but what are the difference between these three? Right? The first is NAND or implementation. The other is black elongated driver nanomagnets. The other is 45-degree oriented. The other has only 5 nanomagnets, right? For one majority logic gate. Now what we have proposed is using this only one 5 nanomagnets, we will be achieving what an address is. Next slide. So this is a basic majority logic using this magnetic quantum dots and how it appears. We can see the same truth table repeating, right? Even for the convolution, we will have this truth table. And this is one patent is there from University of South Florida, where they wanted to use this magnetic co-processors for image recognition. For this Google map, they take a particular image and using they are trying to match that pixels using this magnetic co-processor. This is an area where they wanted to see how it has its applications in variety of nanomagnets. See, in 20 level, you can see 59 nanomagnets, right? For one bit. Next one. In 2012, you can see how it has further modified. Next one. 2013, small reductions. Next one. In 2017, this is the state of the art that we started. And 21 into 4 nanomagnets are one bit added. Next one. So with this basic goal, area efficient, speed efficient, energy efficient, we are going to model the devices. Next one. Next. Previous one. Yeah. We can see from 2013 and 2017 what is proposed in 2020. The same function can be done using only 4 nanomagnets. Now, all reduction because using that one slide and turn a map came up. How many of you are aware? Second semester students or third some fourth some will be aware of K-map, right? Basic Boolean logic optimizations. Using that, we are able to build a circuit which has only 4 nanomagnets performing an accurate addition. Taking the literature where it has 25 nanomagnets doing the same thing. Right? Next slide. So we have been performing convolution. As I said, convolution is broken into multiplier. Multiplier is broken into adder and logic gates and adder. Adder is comprising of all this logic. So with this, I put an end to this and it is open for interactive session where this is one area where you want to pick it up from universal logic gate till an adder, how it is done, the workflow which you can integrate. Previous slide and you can stop on the previous slide. Yes. So this is the whole summary. You started from the universal logic gate and you use the same universal logic gate to perform an approximate runtime reconfigurable. And both are same now. Using that you can perform this. This is runtime reconfigurable. So we can have some queries if you have, or we can also take some discussions on this. So we have two immediate tasks for VNR, BGT undergraduate student. One is this radio show, which Dr. Trimalchar is going to force you now. We want 2 to 3, 4 to 5 presentations from you talking about advanced technical concepts using a report. Okay? As I said, you can relate any simple analogy. As I explained interrelation company using biryani, as I explained, we are going home concept with F is equal to A plus B dot C bar. Right? I remember F is equal to A plus B dot C bar anytime, even in my sleep. That's a basic fundamental equation. Everywhere you solve it. F is equal to A plus B dot C bar. Simple. I can go home if it is a Sunday and holiday with no assignment and no assignment. Okay? So like this, I want you to make technical concepts simpler and see how the other task you can also use is how this logic gates, as I said, from the universal logic gate to approximate adder, how this logic gates can be combined to perform any complex machine learning algorithms. Settling machine is another concept which we can explore. Right? We want another one minimum project, mini project, and Dr. Thermal sir and me will be co-guiding initially, and we can target a nanotechnology magazine out of it. This is a plan, two tasks for Veena and Vijay undergraduates, which I want you to take up on very seriously. Okay? Thank you. You are a good audience. Thank you. Very sorry. But just this the person who is actually creating the books in AI and the quantum computing, not only using tools, more than creating.